because I want to get invited back next year.
Is this level?
So here you see the geocentric model. The Earth is in the middle, the sun is going around, and it's carrying the planets with it. Okay, that was the model invented by Tycho Brahe around 1590 or so. So, and this was the model that all the Jesuits were flocking to after Galileo, because this model showed how it could work, at least geometrically. Okay? If you want to see how simple it is, watch this little trick. See, all we do is change the centers, and we start the whole thing all over again. See? So there's really no difference between the two models at all, geometrically speaking. Either model can work. And at that time, in the 1500s and 1600s, nobody really knew a lot about forces and gravity and things like that have to be taken into consideration. And so the side of the Catholic Church that was going to stay devoted to the fathers and the popes, this is what they used. Okay? Now, as a matter of fact, even when the issue of the forces and the gravity came into play in which model you would choose, there were such staunch defenders of the Catholic decision to condemn Galileo that on the opening pages of Newton's Principia Mathematica, that was his famous book, 1687, that basically changed the whole world. And it talked about gravity and forces and things of that nature. Okay, this was a monumental book. Nobody had ever written anything like this before. Okay, it explained to us why an apple fell from a tree. You know, the old story about Newton sitting under his tree, apple tree, and the apple falls and hits him on the head and wakes him up. And he begins thinking about gravity. What made the apple fall from the tree? Why did it go down? Okay, that was our, you know how, and the guy who discovered buoyancy and density, what was his name? Bernoulli, I think. Bernoulli, I'm not sure. Anyway, he yelled, "Eureka!" when he was in the bathtub, naked in the bathtub, and he was playing with some soap or balls or something, and he finally had this insight into what caused, buoyancy and density and all that kind of stuff. And prior to that, people just watched these things occur, but they didn't know how to explain them scientifically. What made something do something and not something else, okay? So that's why the scientific revolution was so big, because it finally gave us an insight into why things were happening instead of just happening, okay? So that was before what you're seeing on the screen here. Okay, so it's easy to adjust these things geometrically. The question is, can you make it work by dynamic forces? Okay, and by that we're talking about gravity, number one, and let's say centrifugal force. We've all felt that, right? When we're traveling down the road and you take a sharp corner, your whole body wants to go to the right side if you're turning left, because that's a centrifugal force. Centrifugal means away from the center, okay? And then you have this other force, inertial force, called Coriolis force. And a Coriolis force is what makes our hurricanes turn left or right, okay? They turn left in the northern hemisphere, and they turn right in the southern hemisphere. And then you have to be a powerful force in order to make those hurricanes turn one way or the other, okay? So that's another force we have to deal with. But at this time, when these models were made, they didn't know anything about forces and gravity, okay? At least not in the mathematical sense. When you can put ideas into a math equation, and that math equation represents the reality, okay, that says something, right? But, as much as we praise Isaac Newton for discovering gravity, All he really did for us was tell us how fast it reacts. He didn't tell us how gravity works. He had no idea what makes an apple fall from the tree. Okay? He didn't explain it. He says, I'm not here to explain that for you. All I can tell you is how fast it falls. And it will fall the same rate whether you drop it from 100 feet or 10 feet, or whether you drop a rock or a feather or whatever it is, it's all going to fall at the same rate. 32 feet per second it's going to accelerate. And that's what we have. Okay? And then he made another equation, very famous equation, called F equals ma, force equals mass times acceleration. Probably the most famous equation ever in the history of the world. Because with it, we can send up satellites and we can determine how fast the Earth, sun rather, is going around the Earth. And you can tell how fast the planets are going around the sun. But even that equation isn't all it's cracked up to be, because that equation doesn't cover everything that's happening. And the fact is that when they send up those probes and satellites, they have to add in certain forces. One of them is that centrifugal force I was telling you about. The other is the Coriolis force to make those probes react right. Okay, so as good as F equals ma is, it's not ubiquitous in the sense that it covers all the areas that we need to cover. In the history of this, there's also, now how do I get out of here, and then what do I do here? Someone help me. So I want to go to the menu where this stuff is. That's it, yeah. All right, so let's look at one matter that has come up since there's been somebody who wrote a book just recently. His name is Father Paul Robinson. And the book is titled The Realist Guide to Religion and Science. Yes, thank you. And he's from the SSPX, and he does a fantastic job on the philosophy, history of philosophy, and Aristotle and Aquinas and all that. But when it comes to cosmology, he went off the track. And he remains a diehard heliocentrist. And the only proof that he put in his book, this was written, published this year, I think. And I've been in contact with him, so he knows who I am and I know who he is, and the war is just starting, and I'll let you know how it goes by this time next year. And the only proof that he used for his heliocentrism is this thing called stellar parallax. Anybody ever heard about that? Okay. Well, that's an old proof, or an old attempted proof of heliocentrism, but it's been discredited. It doesn't work. It doesn't prove heliocentrism at all. Okay? All it does is show us that same basic thing I was trying to tell you before, that in order to get to 4, you could add 2 plus 2, or you could add 3 plus 1. Okay? Both of them will get you 4, but the question is, $64,000 question is, which addends are correct? Okay? You have 3 apples, one pear, or do you have 2 apples and 2 pears to get to 4? And it makes all the difference in the world. Okay? So your result, in other words, the answer is not justify the means. You've heard that old saying, right? Okay, so let's look at parallax, for example. Now he's got so many. I mean, I designed all these, but we tweaked them as we went along, and I forget which one was the best one. I think, let's try this one. No, that's not the right one. Let me go back here. That might not be the best one either. Just give me a moment here. the left-hand side, let me make that a little bigger for you. Now where to get it?
Just cancel it out.
I just canceled it out, okay. What was I on, this one? It's HD. Okay. Is there a way to expand this without going through all this meticulous? All right, so on the left-hand side, the Earth is going around the sun, and you have two stars, okay? One farther away from the Earth than the other. And if we analyze these two stars over a 180 day or so period, we see that as the Earth moves, the angle that we see both stars changes. That angle is called parallax, okay? So this is how we look at it from Earth. From that black box up there, you see the nearer star is shifting back and forth against the farther star. All right? Everybody understand that? Any questions on that? All right, so what we do with the geocentric, since the universe is rotating around the Earth, and the sun actually is going a little slower, this is what's happening in the geocentric. The universe is rotating left to right. Of course, it's right to left for you, but anyway, I'm going to do it from my vantage point here. And the sun is going with it, but it's going a little slower every day, okay? And that's how we get our 365 days in a year. Because the sun goes 4 minutes slower than the universe does in the rotation, okay? And that makes the sun go through the zodiac, the 12 constellations of the zodiac. Okay, so as the sun is moving in this backwards motion, it's going to do it in 365 days, and it's carrying the whole universe with it. And we're going to see the exact same parallax angle as we did in the heliocentric version, if you compare the two black boxes up top. Okay? So it's easy to see here, that's all geometry. Okay? Anybody have a problem or a question about that at all? Okay, great. So, that's all I'm going to show you for now. Then I'll get to more later. I want to go back to my old friend Einstein. Okay, so there was another experiment done, and who remembers what the last experiment I told you about was? Anybody? Let's see if you're paying. Airy's failure, yeah. And remember, he had two telescopes, and he expected that the one that was filled with water would make the light go slower, and therefore would not hit the eyepiece of the telescope. And if that was the case, he thought it was going to hit the side of the telescope, and if that was the case, then the Earth was moving. If it hit the eyepiece of the telescope, the Earth wasn't moving. Okay? You can look that up on your own on the internet. Okay? Now, so that was 1871, and then there was another experiment done in 1881, 10 years later, by a man named Albert Michelson. He was a world-class physicist. In other words, he's very famous for his previous work, and it was funded it was actually recommended to do by James Clerk Maxwell, who was a prestigious physicist in the 1860s. And he gave us Maxwell's equations, which we still use today. And so there's some very famous men behind this experiment. It's done in 1881. And what they did was they set up this thing here called an interferometer. And basically, the light comes from a light source. There's a mirror after that the light splits. and one light beam goes one way, and the other light beam goes that way. And then they make this light beam go back and forth a few times, give it some distance. And then the question is, which light beam is going to beat the other back here at the microscope, up there at the center? Okay? So the theory was that if the Earth is moving, then the light beam that is discharged from this machine that goes in the direction of the supposed movement of the Earth around the Sun, which is pretty fast in their framework, which is 19 miles per second, or 66,000 miles per hour. That's a pretty good clip. So if this light beam is going in that direction, and the speed of the Earth is going in the other direction, so let's say the speed of the Earth is going this way, and I shot the light beam that way, well, the space should impede that light beam to a certain extent. And you can actually calculate to what extent it would be impeded, okay? And so they expected that the light beam that was shot with or against the Earth, didn't matter, would be affected, but the light beam that was shot this way, that didn't go with the Earth's path, okay, would not be affected. And they ran this through everybody, and everybody said, yeah, that's the way it should work, okay? It's just like if you were a swimmer, you're in the water, and let's say the water is coming at you, and you're trying to swim against the water, like the salmon do every year, right? And they just inch up, you know, because they can swim a little faster than the water is going down. Well, that's going to impede your speed, correct? The fish are not going to be going as fast in the water if it's going against them, okay? So everybody thought that since the Earth was moving, they should see this wide gap between when these two light beams would reach the microscope. Should be a wide gap there, obvious gap. All right, and what did they see? Anybody want to take a guess?
So that gap is supposed to be caused by the ether, right?
Well, let's just say the speed of the Earth against the ether. Well, if you want to add the ether in there, let's do that. They all thought that ether was there, and they had evidence for it, and that was even in Maxwell's equations, as a matter of fact. The whole thing was based on ether presence. So that was the going science at that time. All right? And that'll become important later when we talk about Einstein. So for now, let's just say that the beam going against space or ether, whatever you want to call it, okay, due to the revolution of the Earth around the Sun, is going to go slower, and there's going to be a wide gap between those two light beams coming back at that receiver. There should be, if the Earth is moving around the Sun. So again, let me ask you, what did they see? Almost equal. Almost. And that will become important too. Okay, they saw about 1/10 of the speed that it should be. Okay? 1/10. So they had 1/10 of a positive result. All right? And that'll become important later. But let's say for practical purposes it was 0. And what does that tell us? If both those light beams came back at the same time at that receiver, what does that tell us?
The Earth is stationary.
The Earth ain't moving. That's what it tells us. Okay? The Earth ain't moving. Okay? Now these are world-class physicists doing this now. So they were scratching their heads and figuring out what the heck is going on here. And so they decided to do it again. They did it 6 years later, in 1887. And they got Alexander Graham Bell, who was probably rich by this time with the invention of the telephone, to fund the whole thing. They made the instrumentation much more precise. They put the whole table in a mercury bath, which cost a lot of money. They made sure that vibrations as close as 500 feet away would not be felt. So they put this whole thing in a basement because they figured there was some kind of external interference causing this weird result that the Earth wasn't moving. Okay? So they did the experiment in 1887, and by this time Albert Michelson took on a partner. His name was Edward Morley. another top-class physicist. They did the experiment again, and let me ask you, what do you think the result was? It was even worse this time than it was the previous time.
0.1%.
Yeah, just right around there. You know, so hey, if you're going to make more precise instrumentation and the Earth isn't moving, what do you expect? You're going to get a more precise result that the Earth isn't moving. Okay? That's just the way science works. So that's what we call the data. That's the data. And next comes the interpretation of the data. Okay? So, this was a real head scratcher for them. Because by all intents and purposes, that ether, that space should have impeded that light beam. I mean, because all of Maxwell's equations were based on that. And everything they know about science was based on that. They could explain electromagnetic activity, magnetic activity. They could explain pressure, and all kinds of things they could explain by that. But here it was. It defied everything they knew previously. And so another scientist came along about 5 years later. He was in contact with Albert Michelson. And in my book, I have the actual letters that they wrote back to each other, back and forth to each other, in their own handwriting. Okay, I had to go to a special museum and look at the microfiche and search for those, and I did. It took me weeks to find them, but I did. And so they're all in their photocopy for you in the book. And so Lorentz is writing to Michelson, he's writing to Oliver Lodge, which was another premier physicist who lived in England, and said, what gives? Can you help me explain this experiment? And nobody could do it. Nobody could do it. So Lorentz, forced to come up with an answer, Hendrik Lorentz, a Dutch physicist, very famous, knew Einstein and everybody else around that area. He came up with a theory, and he said, okay, the reason those light beams did not come back to the source at the same time is not because the Earth isn't moving, it's because the length of Michelson's apparatus shrunk during the experiment. Okay? If you believe that, when I got some land in Florida, I'd love to sell you in the central part of it. Okay? So in other words, what he's saying is that the length of, let's say the red lines, the length of that red line was shortened because the whole experiment shortened at that point. And the yellow barriers were not affected. They didn't shorten. Okay? Does that sound cogent to you? Not really. So, because it's like, what would make it shorten? But that's the only answer that they could come up with. Okay? That space shortened somehow and made that light beam come back at the same time as the other light beam. Okay? When the logical interpretation of that data is that the Earth isn't moving because there was no pressure on the light beam. Okay? So you see how you can have two different pathways to the same solution? Okay? The solution is make sure those light beams coincide when they get back to the receiver. Someone could say, well, it's because the Earth doesn't move. The other guy says, no, that's because the whole interferometer was shortened. All right? And so that was the going. As a matter of fact, there was another physicist in Ireland. His name was Gerald Fitzgerald was his last name. John, I think, was his first name. And he said, you know, I've used your explanation for the Michelson-Morley experiment, that's what this was called, and they laugh at me over here in Ireland. And he goes, but now that you say it, I will laugh at them for saying that the instrument can't shrink. And so we had the beginnings of a theory that had absolutely no proof to it whatsoever. Okay? Because nobody measured the distance between those two blocks in the red light zone there, to determine that something shrank. This was all theoretical that we were talking about. This means that they said it has to be this way, that the instrument has to shrink in order for us to explain the result of it. Okay? Everybody with me? Okay. So this laid around for a while, and they were still wondering whether it was right or not. And then comes along this guy named Albert Einstein. And Albert Einstein knew about the Michelson-Morley experiment, although they try to hide that from us today. They try to make it sound like Einstein invented a special relativity theory because he was looking at Maxwell's equations from 1865, and that would give it a little bit more prestigious appeal, you see, because it would show that he wasn't trying to have another answer to why the Earth stood motionless in the center of the universe. Because if people caught on to the fact that he was inventing special relativity to deal with this issue of the Earth being motionless, well, that makes it a whole different ballgame, you see. But if you can make it look like he's dealing with Maxwell's equations, well, that's only up and up, okay? But anyway, so as a matter of fact, in his first sentence of his famous 1905 paper, the electromagnetic dynamics of moving bodies, somebody in the last period thought I said human body. Must be my, I don't know. Anyway, in the very first sentence, he says, since tests on the Earth's motion have been inconclusive, something to that effect, I am developing this theory of special relativity. So he comes and tells us, you know, why what the motivation is. Okay, because these experiments show that the Earth isn't moving, but we know it's moving. And how do we know it's moving? Because Copernicus told us. Okay? That's what they were all saying at that time. We've believed this for so long, and we can see the motions of the planets and the stars all coincide with this heliocentric view. Nobody ever proved it. They came up with proofs like I showed you before, like stellar parallax. And at that time, nobody knew that there was a reciprocal to stellar parallax on the geocentric side. So everybody just believed that we had the proof of heliocentrism based on stellar parallax. Okay? But there was no proof. But can you imagine a world that would be turned upside down as much as it would be if everyone found out that science had been wrong for the last 300 years and the Earth was really motionless in the center of the universe? What kind of world would we have? Have you ever think about that? Everything would be changed. Everything that we do. And we would be headed back to God and the Bible and the saints and the fathers. This whole world would be changed. Okay? I can't think of anything that would be more monumental than that. That the Bible was right when it said the Earth doesn't move? Are you kidding? Wow. And the church was right for condemning Galileo? And led by the Holy Spirit who wasn't on vacation in 1616? Well, that's comforting to know. Can you think of anything else that's going to change the world besides that? I can't. So a lot was at stake. And at this time, the evolutionary theory had risen its ugly head, and it was a two-headed monster now, Copernicanism and Darwinism at the same time. So any scientist worth his salt, with pride and the fact that he has his sheepskin on the wall from the famous university, he's not going to get into this stuff. So we've got to find a solution to this experiment. After all, we're scientists. All right? Everybody see the dilemma here? The tension that's going on? Okay? So, Einstein comes along, he writes his paper, and he says, yeah, I think that length contraction is a great idea. I think that's actually what happened. And he had no proof either. Wow, that's interesting. Science succumbs to a hypothesis that it can't prove to one of the most important experiments ever done in the history of mankind. whether the Earth is moving or not. Can you think of a more profound question of whether the Earth is moving or not? And so they're now going to depend on a hypothesis that they say must have happened? Not quite. So what dilemma did Einstein get into with this? Well, the dilemma was, if you say that the equipment shrank in order to produce the result, what does that mean? Well, it means you also must dilate the time. Okay? Think of it this way. Here's point A, and here's point B. Okay? So you have a block of wood going from point A to point B. So if that block, as it's moving, shortens in its length, how much time is it going to take to get to point B? No, it's going to take more because it's shortened. The tip of the block is now shortened. So to get to point B, you're going to have to dilate the time. You're going to have to increase the time that it travels to get to point B. Okay? That's a natural consequence of saying that the length contracted in this experiment. See, there are consequences to your answers. You may make up the length contraction, but you're going to have to pay for it with time dilation. Okay? So that means time is not absolute. Time is relative. Length is relative. And if you have this block of wood, and it's traveling to point B, okay, and it's shorter than it was before, what is the mass of that object going to be once it reaches point B? Anybody? It's going to be more. Because now it's smaller, you see? Its volume is smaller, so that means it's denser. So that means it has more mass per unit volume. So now you have mass increase. Okay? Now you have another problem. Mass increase. Now, in order to get there, in order to have all these ad hoc adjustments, length contraction, time dilation, mass increase, what else do you have to do? They weren't out of the woods yet. Say again?
Velocity has to slow down.
No, just the opposite. C, the velocity of light, has to be constant.
Yeah, C has to be.
Yeah, what did you mean then?
The velocity of the object.
Velocity of the object, okay.
You slow it down.
Well, it's, we're just taking an arbitrary velocity. It doesn't matter what the velocity is, yeah. Okay, so C, that is the speed of light, has to be constant. In other words, this is what happened, folks. You had two choices after this experiment. Either light is constant or the Earth is constant. And by constant, I mean it doesn't move. Okay? Those are your two choices. And what do you think Albert Einstein's going to choose? Okay, his wife became Catholic. He was an atheist, a practical atheist. He followed Spinoza, and we heard about Spinoza today and yesterday. Okay, that was his mentor. All right. He divorced his wife, married his cousin, and was infatuated with her daughter, and then divorced his second wife. Okay, and there's all kind of chicanery going on. And he had no love for Catholicism. He hated the Catholic Church. He hated Christianity. And I can prove it to you. It's in my book. You can go read about it. So what do you think he's going to choose? Is he going to rehabilitate the Catholic Church and say she was right in condemning Galileo?
No.
Not on your life. Okay? So you stick with this, what is now called a special theory of relativity. Okay? We want to apply a name to it, because that gets us out of the problem, even though it's a haunted house of mirrors. Okay? Where everything is not what it appears to be. If length can contract and time increases and mass increases and the speed of light is constant, no matter what happens, then wow, we've just changed it. We've reinvented physics from the bottom up just to take care of this problem that the Earth isn't moving. Okay? That, my ladies and gentlemen, is the legacy of Albert Einstein and special relativity. It was all invented to keep the Earth moving because the experiments showed it wasn't moving. Okay? I can go into a lot of detail for you, but that's the gist of it. Now, here was a problem. As we talked about, if you invent a solution that's not a real solution, you're going to have many problems. And here was another problem he had. This little world he created for himself where length contracted, light dilated, time dilated, mass increased, and light was constant speed, was only in an inertial frame of reference. Now, an inertial frame is defined as either being at rest or moving at the same speed. Okay? So, for example, if you're in an airplane and the airplane is moving 500 miles per hour, but it's uniform speed, constant speed. Okay? That would be an inertial frame. So if you threw a ball up in the plane, it would come right down to your hand. All right? A non-inertial frame is one in which that airplane is accelerating or decelerating. So if that plane is accelerating and you try to throw a ball up, well, that ball's going to be affected. It's not going to hit your hand on the way down. Okay? You can tell this when you drive a car or, you do anything, basically. You're going to be confronted with those forces. They're all around us. Okay? So here's the issue. If this was invented, this whole length contraction, time dilation, all this stuff, where's the inertial frame that you're talking about? Where in the universe is this inertial frame? There is none. Why? Because that universe is filled with gravity and inertial forces everywhere you go. So there is no inertial frame to test whether this is correct or not. So he's basically invented, by a thought experiment, what would get him out of this dilemma without any proof whatsoever. Okay, now some people might say, well, when they accelerate a proton in a cyclotron, it gains more mass. So that proves Einstein's theory. No, it doesn't. See, this is another situation where you have 2 plus 2 or 3 plus 1 equals 4. Okay? If that proton is moving really fast, it's moving fast through something, and it's picking up that something on the way to the other side of the cyclotron, and it's going to have more mass. Very simple explanation. Okay? Because space is not nothing. Space is a something. Whatever it is, it's a something. Okay? So it's picking up. There's an easy explanation. But they can't explain length contraction or time dilation. Okay? That's their problem. They can only do it in an inertial frame, and there are no inertial frames. Because the universe is not an inertial frame. Okay? It's a non-inertial frame. And that makes all the difference in the world. So, what happened to little Einstein at this point in time? Well, everybody was cogitating on this special theory, and so was he, until they all found out that it didn't work the way they thought it should work. And so they had to invent another theory to cover over the mistakes of the first theory. And that was 10 years later in 1915. And that's called the general theory of relativity. Okay? Now, the general theory of relativity went in one right direction, and that is, it said, look, we got to deal with these non-inertial frames. Gravity and inertial forces. We have to deal with them. And guess what happened when he did that? When he incorporated gravity and inertial forces into his theory, his relativity theory, what he found was that you could put the Earth right smack in the center of the universe, motionless, and have the universe rotate around it on a daily basis. Surprise, surprise. Okay? When you deal with the real things that are out there, that's where it led back to. But his general relativity, now the key word there is relativity, allowed him also to say that you could have the reciprocal of that, which is an Earth rotating in a fixed universe. Okay? And he would work out the math where that would be possible too. Okay? So there you have it. The very theory that he invented in 1905, special relativity, to take the Earth out of the center, was now overturned in 1915 with his second theory, general relativity, that put the Earth back in the center. It was just a matter of which one you wanted to choose. Did you want to choose the biblical one, where the Earth is in the center and not moving, and have the universe rotate? Or do you want the one of modern science, where the Earth is rotating in a fixed universe? Which one do you want? Well, which one do you think they were going to choose? Okay? So then we had another experiment come along, and what do I have to watch till 2:30? 2:30, okay. Don't fall asleep on me now. Okay, everybody keep awake. Is it hot in here, or is it me? Is it hot? Huh? After lunch, maybe that's it. Okay. Anyway, hang on. I got some exclusive information for you. You can't get anywhere else. You're going to want to hear this, okay? All right. It is another experiment. The same guy, Albert Michelson, he did another experiment in 1925 with the same kind of fix-up here, okay? But this time, he was going to test for the rotation of the Earth, not its revolution around the sun, okay? Did the experiment, and Einstein knew about it, a lot of people knew about it, and what did they find? They found 98.7% of what they call sidereal rotation, okay? That means they almost got 100% of a rotation, 24-hour rotation, okay? Now that was a perplexing little piece of information. The first experiment we did in 1887 showed that the Earth was not going around the sun, it was motionless. The second experiment we tried with the rotation now shows us that the Earth is spinning around 24 hours. Now how can that be? Okay, now, if you're a heliocentrist, this is not good news. You may think it's good news because, wow, we finally found, one of our components, that the Earth is going around 24 hours. No. It doesn't work that way. Because if you're a heliocentrist, you need both a 24-hour rotation of the Earth and you need Earth that goes around the sun in 365 days. If you don't have both, you don't have a system. Why? Because we have to explain the seasons. See, the rotation of the Earth only explains the day-night rhythm. It doesn't explain the seasons. In a heliocentric view, the Earth is tilted 23.5 degrees on its axis. It always points to the North Star, and that's how we get our seasons. But if the Earth isn't moving, you don't get any seasons, no matter how many times it spins around per day. Okay? So this only tightened the noose on them even further. Because what was the geocentric answer to that? Well, the geocentric says, hey, this is right up our alley. This is positive proof that geocentrism is correct. Because we don't need to have an Earth going around the sun, obviously. Okay? All we need is one motion. All we need is a universe going around the Earth in a 24-hour period. Actually, it's 23 hours, 56 minutes, and 4.1 seconds. Okay? That's all we need. And all we need is the sun to go up and down at a 47-degree angle in that circular motion of the universe, and voila, we have geocentrism. But you heliocentrists have a problem, because you need a revolution and a rotation, and you only have a rotation. At least if you look at the experimental evidence. Okay? So geocentrism, hands down, beats heliocentrism, because we can answer all the questions that come up. Okay? And we don't have to create fudge factors like time dilation and length contraction and all this stuff. Or dark matter, if you want to add that in there, or dark energy, or all that has to keep the universe expanding. because we don't need an expanding universe. Okay? And what else did Einstein's general relativity tell us? Well, it said that if you have a rotating universe, you also have great centrifugal forces on the outer rim of that universe. You know, like if you're on a merry-go-round and you're out on the rim of the merry-go-round, what happens to you? You have a force that wants to pull you off, but if you go into the center of that merry-go-round, you hardly feel it, right? That's called centrifugal force. So if you go, and if the universe is rotating and you go on the outside rim of that, or near the outside rim of that universe, you're going to have tremendous centrifugal forces. And Einstein said, yes, that's correct. You will. And what's going to happen to the speed of light? Well, if you increase the centrifugal force, you increase the speed of light. So it's not constant. Because where centrifugal forces are, that's a non-inertial frame. And the speed of light is only constant in an inertial frame, not a non-inertial frame. Okay? So you can see how convoluted this whole thing is. All right? But in the scriptural, the ecclesiastical answer is very simple. The earth isn't moving. It's not even rotating. It's not revolving. It's still. It's fixed. It's immobile. And so much so that God uses it, as I said, as an analogy for his own immutability. Because it can't move. All right? So, let's look at, I got 10 more minutes, or 6 more minutes, looks like. So let's look at some other issues here. Did anybody drive here from wherever you are to get Conception? Okay. Did you use the GPS in your car? You did? Okay. Well, let me tell you something about that. Here's a real story for you. Global Positioning Satellite, that's what the GPS stands for, okay? Now there's like, 24 of them up there. They all send signals back and forth to each other, and they have a ground station that's involved, and that sends signals, blah, 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 okay? Now the GPS, and this is one of the reasons, or one of the top topics in our movie that we put out in 2014 called The Principle. In case you haven't seen it yet, you can order it from www.theprinciplemovie.com. Okay? And it was a theatrical released movie back in 2014. And one of the topics that it covered is the one I'm going to tell you about right now, along with some other ones that I don't have time to tell you, but wish I did, maybe next year. Anyway, the GPS is important because the GPS satellites, in order to communicate with each other, send signals back and forth. And those signals go with the speed of light, which is 186,000 miles per second. Okay? But they have a dilemma. Because if you have a satellite in the east communicating with a satellite, GPS satellite in the west, and this one in the east sends an electromagnetic wave to the one in the west, east to west, and then you compare that speed to the speed that the one in the west is going to send to the one in the east, they're not going to be the same. Okay? And they will differ by 30 nanoseconds, 50 nanoseconds. Nanoseconds are pretty small, but if Einstein's theory is correct, then there should be no difference. Okay? But there is a difference. As a matter of fact, the reason we found out this is we contacted the guy who built the GPS. His name is Neil Ashby. He's in charge of it, at least at that time. And he even admits that there's a discrepancy between east and west flow and west to east flow. Okay? And you're going to see in a second why this supports geocentrism. And we contacted another individual, a physicist who works for Navcom Technologies in California, but he's retired as of last year. And he contracts with John Deere Tractor. And you know today how they have tractors in the fields that are unmanned and they're controlled by the GPS, okay? So our friend, Ron Hatch, who works for Navcom, as I said, he had to go into the GPS computers because he had to program the tractors for John Deere into the GPS to make sure everything was only up and up. And if you don't do that, what happens? Well, your tractor goes into the ditch instead of plowing your field, okay? So you have to get this thing right. And so there's where Ron first noticed that, and by the way, Ron is not a geocentrist, okay? But we use this information. Remember I talked about using the data of science to prove our claims. We know the science better than they do, okay? So Ron told us he had to go in there and he had to put a correction into the GPS system. And that correction came from an experiment done in 1913 called the Sagnac experiment. And Sagnac found that the speed of light was not constant. Okay? Neil Ashby mentions the Sagnac correction. Ron Hatch mentions the Sagnac correction, all to do what? To compensate for the fact that east to west signals are faster than west to east signals in the GPS, which all contradicts special relativity. Okay? So what happens in society is, in the newspapers, is they pre-program the GPS computers with the Sagnac correction to make it look like everything is normal and the light speed never varies. And guess what? And this supports the special theory of relativity that says that light speed is always constant. You guys get that? Huh? You guys get that? Listen to that. What they're doing is they're fixing their problem. They're not telling you about it, and then they say, and to fix it, we have supports Einstein's relativity theory, so everybody can go on worshiping Albert Einstein. And we'll never get to the truth. And what is the truth? The truth is that the earth isn't moving. That's the truth. That you can depend upon. That you can take to the bank. And we can prove that easily, scientifically. And I can give you reams. That's why those books are so big. Because I go to every experiment ever performed to show you they all have the same result. Okay? Every single one. I go through every wrinkle of the church's history about this issue so that we miss nothing. You have it all to show you from scripture, from church authority, and from science that, yes, we've all been bamboozled. Okay? Now, I have a minute left, so anybody have a quick question? Yes, sir.
Just speak just a minute about pole shift. I believe, I agree with it. Let's say like pole, are there poles, and are there pole shifts? And is there a need to talk about poles or pole shifts if the earth is?
Sure you can. You have magnetic polar shifts in a lot of places. It could happen here. It hasn't, but it could happen here. But it has nothing to do with whether the earth moves or not. Yes, sir. Back there. Checkered shirt. He doesn't know I'm calling him. Yeah, you had a question?
Yeah, it's gone now.
What's that? Oh, it's gone. Okay. Anybody else, quickly? Yes, sir.
Mine is an appreciation because this Galileo affair is one thing that mainly people opposed to the church teaching and the church's position in many respects.
Yes.
Use. I told Hugh one day that one of our lecturers would argue that, you see, if the church was wrong, since the church was wrong in the Galileo affair, that the sun, that the earth is actually static and the sun rotates around the earth, the church could still be wrong, and indeed is, in abortion and contraception and homosexuality, among other things. So little did I know, and actually totally did I know, I didn't know completely that Galileo was wrong. And had I known, of course, I would have left my lecture dumbfounded.
Well, let me reinforce something from the early part of my lecture in the last session, which was, we can't look at science as objective. There is an evil intent. Not all the time, but a lot of time. There's evil intent because they want to get to a certain conclusion, and they will get there come hell or high water. And they know you don't know about this stuff, okay? So it's like anything else in life. Money, sex, it can be used for good or it can be used for bad. Okay? So let's not leave science out of those two categories. Okay? That's the main message I want to get across to you. Anybody else? You remember your question?
No, but I have a comment.
Okay.
I just remember my life maybe I accepted this whole immutability of the speed of light. Yeah, we hear that God is light. But I think what I'm just realizing, light is a created thing. But that whole idea of God is light and the speed of light is immutable kind of go together. Do you understand what I'm saying?
Yeah.
So that's why, for me, I'll say, oh, that makes sense. Like,
Yeah,
the speed
yeah.
of light is constant. Well, God doesn't change.
Yeah,
No matter where you are, it's
you
the
can build an
same.
analogy on that, yeah. I can see that.
but
Let me give you something else here
That's
that's
how my
very
mind's
important.
ready to justify.
I know I'm going over this, won't take but a second. And they contradict themselves, because in the Big Bang, it doesn't happen fast enough in order for them to form the galaxies and planets and all the other stuff that they want. So they have to supercharge it. Okay, but if they supercharge it, then they're going against the limited speed of light. Not only for light, but for gravity. Okay, so what they do is they ignore all that. They create this thing called inflation. That it inflated to 10 to the 35th power in 10 to the minus 35th seconds. That's because they needed it. Okay, they couldn't build their universe unless they had it, but it violated the special theory of relativity. Oh well. We'll just make it happen real fast so nobody notices, and that's exactly what they did. It's just like a magician. His hand is faster than your eye. Okay? Then, when they get to the part that the universe has to expand, and this happened, with Hubble, and I can tell you a whole story about Hubble, but, and then in 1998 they saw these supernovas, supernova 1A, and they said, well, the universe is really expanding faster than we thought it was expanding, and it's accelerating. Okay? So first of all, they had to invent dark energy to keep it accelerating, and they've never seen that, okay? But they need it for their theory. And second of all, how fast is that expansion going? Well, it's going way past the speed of light, I can tell you that, and they admit it. So what do they do? What do? They abandon the special theory of relativity and they go to the general theory, because the general theory said light is not constant, they can travel any speed. Okay? So we're talking about, what do they call it? Triple Monty or something? I mean, they're just bamboozling us with all kinds of stuff. And who's going to ask the questions? There may be somebody like me. Who's going to listen to me, though? And maybe you guys are. Okay? Maybe they'll listen to our movie a little bit, but who knows, man? They trounced that thing as fast as it came out. All right? So, there we are. Yes, sir.
Just got to clarify, that speed of light is for a vacuum, and light does change in different mediums. So it's different in water, different in air, different in glass.
Oh, sure, yeah.
Just to make that clear.
So when I say light is constant, I'm talking about a vacuum.
Vacuum, yes.
I'm talking about an inertial vacuum, okay? Yeah, try to find one of those in the universe.
Well, that's the
Okay.
assumption that the universe is in a vacuum for their theories.
Yeah, they're theories, exactly. But the theory says, general relativity says that light can travel way beyond 186,000 miles a second. Okay? That's his theory. It's not mine. I'm just using his theory to show how jumbled up his whole view of the world is. Okay? And since there is no inertial frame in the universe that I know of, do you know any place that has no gravity and no inertial forces? I don't. So we're going to have to run by general relativity. If we do, then the speed of light cannot be constant, and neither can gravity. Okay? So there we have it. Yes, sir, in the back.
Can geometrically, for example, Neptune be the center of the universe with all the planets rotating around it, geometrically speaking? And same question for Alpha Centauri.
Sure. That's what general relativity tells us. Okay? So what they do admit by that is that it is possible to have Earth in that place. Okay? But I'm not arguing for Neptune because the Bible doesn't say Neptune is the center of the universe. Okay?
How about without relativity?
What's that?
How about without relativity?
I didn't quite hear that.
How about without relativity?
Without relativity what?
If relativity is wrong, based on the evidence we have, could it be shown or inferred that another planet at the center of the universe would be rotating around?
Yeah, I just said so. Yeah, mathematically, geometrically, you can do that if you want. Proving it's another story altogether. Okay? Having the evidence that it's true is also another story altogether. Okay? So, yeah, but that's the dilemma of general relativity. It's like a maze. You never know where you're going. But I'm going to use his information that allows the Earth to be the center of the universe against him. Sorry. And I'm going to use it to show that light is not constant, and neither is the speed of gravity. Okay? I can do that because I'm a scientist. Yes, sir.
I don't disagree, but if the Earth isn't spinning, can you explain how the winds are generated without the Coriolis effect?
There is a Coriolis effect. As a matter of fact, we have the same Coriolis effect to move those hurricanes in different directions as the heliocentric version does.
So you're saying the Earth isn't orbiting, but it's still spinning?
No, it's fixed, doesn't rotate. The Coriolis force comes from the rotating universe. In physics, if you look at Newtonian physics, the angular momentum of a spherical body rotating will create centrifugal and Coriolis forces. And it will create it to such a scale that it will keep all the stars and the sun rotating around the central axis of the universe. Okay? Now there's an instance where Coriolis force and centrifugal force are used as real forces. In the Newtonian framework of just the sun and the earth, the inertial forces, the Coriolis and the centrifugal, are fictitious forces because they can't fit them into the equation. F equals ma. They have to do so by hand. And they have to do it by hand because they can't send up a satellite or a probe unless they add in the centrifugal and Coriolis forces. But their equation has no room for it. Okay, but in the geocentric frame, our equations do have room for the Coriolis force because it's twice the strength of the centrifugal force, and that means it's going to hold all those celestial bodies in a circular motion around the universe's central axis. It all works physically. Okay, we've all worked it out. As a matter of fact, you can go on Wikipedia, look up Coriolis force, and at the bottom it'll tell you that the Coriolis force is twice the force of the centrifugal, and it creates a centripetal force on all the bodies in the universe, which keeps them rotating around the center. I didn't say that, Wikipedia said it. Okay? So there's proof of geocentrism right there, but who can go in there and pull it out and interpret it correctly? All right? But it's in my book. You can see how I do it and how others have done it in the book. There's many more people than me, dozens prior to me, who have done the same thing. And they show how a geocentric system works. Okay, so all the dynamics are taken care of. You saw the geometry all taken care of. Yes, sir, in the back?
Okay. Just a quick question. So you mentioned inertial reference frames.
Yeah.
Can you explain how inertial reference frames work versus just a point in space versus an actual physical object, such as the Earth?
Not quite sure what your question is.
I guess my question would be, inertial reference frames, generally, the definition, there's going to be no acceleration acting on that object.
The what? Stand up so I can hear you.
So the inertial reference frames, you're talking about no acceleration acting on the frame.
No acceleration to do it, no gravity.
I'm just trying to figure out how you're using an actual object as your inertial reference frame, such as the Earth, because you will have forces acting on that object.
But those forces are counterbalanced.
Okay.
That's how.
Okay.
Yeah.
That makes sense.
Okay. All right. Anybody else? All right. We're done. Thank you so much.